Okay, welcome to part 3 for chapter 12. In this video, we're going to talk about LeChatlier's principle. We've been talking about reactions at equilibrium and how we can calculate equilibrium concentrations. In this section, we're going to talk about what happens to a system's equilibrium if you apply stress, right? And when we say stress, we're talking about change. So we're going to talk about how an equilibrium system responds to changes in concentration, to pressure, and temperature. Okay, so first of all, let's go ahead and get started on changes in concentration. All right, so one thing we want to make note of, we want to remember, is that K equals Q at equilibrium, right? We want to remember what Q is. It comes up here. Q is the equilibrium expression, right, when it's not at equilibrium. K is at equilibrium. All right, so what happens if we change the concentration? All right, so if we add more reactant, so what I'm going to do is I'm going to give us like a little fake reaction here. A plus B gives us C. Right, and so Q would be concentration of C over concentration of A, concentration of B. Okay, at equilibrium, that would equal K. So if we add more reactant, then Q is going to be less than K, right, because we're adding to the denominator, right, so we're making that number smaller. So to regain equilibrium, what needs to happen? We have to shift right? So if we add in more products, If we add in more reactants, then the overall equilibrium is going to respond by making more products until we get back to K, until Q equals K again, right? So if we add more reactants, we will form more products. What happens if you remove a reactant? If you remove a reactant, you're making that denominator smaller, and Q is going to be bigger than K, and you're going to see a shift left. You're going to form more reactants. So if you take reactants out, that equilibrium will shift to the left. What happens if you add product? Right? It's the same idea. If you add product, then again, Q is going to be greater than K because you're making now the numerator bigger. So if you add in product, you're going to wind up shifting left again and forming more reactants. If you remove a product, and this is a good technique to form more products, you are going to be lowering that numerator, right? That means Q is going to be less than K, and this will cause a shift to the right. It'll allow you to form more products. Okay, so let's look at... Here's a graph, for instance, of what happens if you add extra starting material. So at first, when your reaction begins, and it appears that in this reaction, we're looking at NO2 making N2O4. So at the very beginning, you have only NO2, no N2O4. As you start to make product, right, the amount of starting material goes down. As you start to make product, it does eventually level off, right, and you get that dynamic equilibrium where the rates are the same. And so the overall concentration isn't changing. Then you notice that this time right here, we have a big spike in NO2. So we've added additional NO2. And immediately the amount of N2O4 starts to go up again until we reach equilibrium again. In this point, the concentrations switch, but we get to equilibrium once these level out again. Right? We see that the equilibrium does shift when we apply a stress like adding a reactant. So let's think through, and here is just a little table summarizing what we already wrote down. let's work through this practice problem. So we're looking at acetic acid and water. Acetic acid is a weak acid. And so in water at any given time, you will have the neutral molecule, H plus, and acetate ion. So what's going to happen to that equilibrium if we add sodium acetate? Sodium acetate is the acetate salt, right? There's sodium ions and acetate anions. And in water, because it's a group 1 metal, it's going to be soluble. You're just going to be adding a bunch of acetate to the solution, right? So we're adding products. If we add in products, what happens to Q? Right? Products increase. Q is greater than K. And that means what happens when Q is greater than K? We're going to shift left. Right? We're going to make more reactants. If we add additional acetic acid, right, now we're adding to the reactants, Q is going to be less than K, and we're going to shift right. We're going to make more products. Now in this last example, sodium hydroxide, this is an interesting one. This requires you to know a little bit of the chemistry. If you add sodium hydroxide, right, you're adding a hydroxide ion, which is a strong base. And you have H plus ions around, and those two actually will react with one another in a strong acid, strong base reaction to give you water. So essentially what you're doing is you're removing products. So by adding a little bit of base here, you're absorbing those protons. That's going to actually cause, right, it's essentially like you are removing product, which is going to cause Q to be less than K and will cause a shift to the right. So by adding a little bit of base, you can shift the equilibrium right, make more products, and increase your yield. So understanding LeChatlier's principle can be really useful if you've got a reaction that equilibrium stops where you're not making as much product as you'd like. What else is going to affect equilibrium? Well, pressure. So we can increase the pressure, and so I want us to make sure that we understand how we can do that. We can adjust the volume. So some problems will use volume instead of pressure when they're discussing it, but it is the same idea, right? Increasing pressure, you can make that happen by decreasing volume, right? You give those gas particles less room to bounce around. You can decrease, right, pressure by increasing the volume, giving more space. So keep that in mind as we talk through this. If you increase the pressure, right, then the reaction is going to shift to kind of minimize that pressure, to offset that. So increasing the pressure is going to cause a shift in the direction of less gas molecules. That'll relieve some of the pressure that you've created by maybe making the container smaller. If we decrease the pressure, then we're going to shift in the opposite direction. We're going to shift to the side with more gas molecules, because now there's more room for the gases to move about. So let's look at this example problem with NO2 and N2O4. Right, this is going to be this little equation right here. You have 2 NO2 in equilibrium with 1 mole of N2O4. So if we decrease the volume, right, we build up the pressure, then that is actually going to push this reaction to the right. Right, so we will shift right, which will make more product because there's less moles of gas, right? So if there's less moles of gas, that would be less collisions with the inside of the container, and that would relieve some of that pressure you just built by compressing, All right, so again, another good way, if we wanted more N2O4, we could increase pressure to make that happen. Temperature is another way that we can affect equilibrium, which is why a lot of times equilibrium constants are given to you at a specific temperature, because it does change when you add or remove heat. All right, so it all depends on the reaction itself, if it's endo or exothermic. So you're going to think about heat as either a reactant or a starting material. So for me, what I like to do is if a reaction is exothermic, that means A goes to B plus heat. Heat is a product, right? So if you increase the temperature, right, increase T, and heat is a product, it's like you're adding more product. And what happens when you add more product? You go to the left, right? If it's already giving off heat and you add more heat, it's going to shift left. Now, if it's exothermic and you decrease the temperature, right, that's like you are removing product, then you will get a shift to the right, right? And you'll make more products, make more B. If the reaction is endothermic, that means it requires heat. So heat is like a starting material, and we give it the same analysis, right? What happens if we increase the temperature? If we increase the temperature, that's like we're increasing reactants. It's going to cause a shift to the right. We'll make more products, right? This is why with endothermic reactions, heating them up can get them to go faster or give you a better yield. If the reaction is endothermic and we decrease the temperature, right, it's like we are removing reactant, and it's going to shift left. Now, what happens? Okay, excellent. And all these slides are going through the same things we just went through. Now, the effect of a catalyst. A catalyst affects rate. So catalysts actually aren't going to affect equilibrium. So catalysts do not affect position of equilibrium. Excuse me. They will affect the forward and the reverse reaction, so they don't push a reaction further to the left or the right. So if you have a reaction that's not giving you a lot of product because of where the equilibrium lies, adding a catalyst isn't going to help you get more product. It'll just help you get there faster, right? So equilibrium not affected by catalysts. That's important to know.